Have you ever wondered why aerospace engineers don't simply solve the range problem of a rocket by adding more fuel? It seems like the most obvious solution in the world. If a car runs out of gas before reaching its destination, you fill the tank. If a plane doesn't have enough range to cross the Atlantic, you put more fuel in it. The logic seems irrefutable. More fuel means more energy. More energy means more speed or more range. And more range means you go farther. But in the context of rockets, this intuitive logic breaks down in a way that surprises even people with solid technical backgrounds. And the reason it breaks down is one of the deepest and most counterintuitive lessons in all of spaceflight physics. Adding more fuel to a rocket not only fails to guarantee it will go farther. In certain scenarios, it can actually make it go less far than if it had carried less fuel. And understanding why requires delving into the most fundamental mathematics of rocket propulsion, a mathematics that has been challenging the intuitions of engineering students around the world for decades. The starting point for understanding this paradox is grasping exactly what happens to the mass of a rocket when you add more fuel before launch. When you add an additional kilogram of fuel to a rocket, you are not simply adding a kilogram of available energy. You are adding a kilogram of mass that the rocket has to accelerate from the moment of liftoff until the moment that fuel is consumed. And to accelerate that additional mass from rest to the velocity it needs to have when it is consumed, the rocket has to burn additional fuel, which in turn has to have been added to the rocket before launch, adding more mass that requires more fuel to be accelerated. In a chain of dependencies that propagates backward through the entire system, and that the Tsiolkovsky equation captures with brutal mathematical precision. The Tsiolkovsky equation establishes that the velocity change achievable by a rocket is proportional to the natural logarithm of the ratio between its initial mass and its final mass. The natural logarithm is a function that grows in a decreasing manner. Every time you multiply its argument by the same factor, the value of the logarithm increases by the same constant amount. What this means in physical terms is that every time you double the amount of fuel relative to the empty rocket mass, you get the same additional velocity increment, not double. And that additional velocity increment has to compensate for the fact that you now have to accelerate all that additional fuel mass from the very beginning, which consumes part of the benefit you expected to obtain. Beyond a certain point, adding more fuel produces velocity increments so small that the benefit in range or payload capacity is negligible, while the cost in structural complexity, load on the propulsion systems, and operational risk increases proportionally. To understand the magnitude of this effect, consider a concrete example with real numbers. Suppose you have a rocket whose upper stage weighs 1 ton empty, and you want to achieve an additional velocity change of 3,000 meters per second with an engine that has a gas exhaust velocity of 3,000 meters per second. The Tsiolkovsky equation tells you that for this, you need an initial to final mass ratio of E raised to the power of 1, which is approximately 2.718. This means you need 1.718 tons of fuel for every ton of empty rocket, for a total of 2.718 tons at the start of the burn. If you now want to achieve 6,000 meters per second of additional velocity change with the same engine, the required mass ratio is raised to the power of 2, which is approximately 7.389. This means you need 6.389 tons of fuel for the same ton of empty rocket. To go from 3,000 to 6,000 meters per second of velocity change, you don't need double the fuel. You need more than 3.5 times more. And to reach 9,000 meters per second, you would need a mass ratio of E raised to the power of 3, which is approximately 20.09, meaning almost 20 tons of fuel per ton of empty rocket, The scale of the problem grows exponentially with each linear increment of desired velocity. And at some point, that exponential growth makes the problem practically unsolvable with conventional chemical fuels. This fundamental limit is precisely why the concept of escape velocity exists, and why reaching it with a single-stage rocket is so extraordinarily difficult. The escape velocity from Earth's surface is approximately 11,200 meters per second. To reach that velocity with a single-stage rocket using the best available chemical propellants, the required mass ratio would be so extreme that the rocket structure would have to be so light relative to the fuel it carries that it would be structurally impossible to build with current materials. It is not that engineers have not tried to build a single-stage rocket capable of reaching orbit, a concept known as SSTO. It is that the mathematics of the Tsiolkovsky equation, combined with the physical properties of available construction materials, makes it an extraordinarily difficult problem at the limit of what is possible with current technology. And for higher velocities, such as full escape velocity, it is directly impossible with conventional chemical propulsion. But the paradox of adding fuel without improving range has a more subtle and equally important manifestation than the one we have just described. It is not just that the returns from adding more fuel are diminishing in terms of achievable velocity. It is that adding more fuel also adds more structural mass to the rocket, and that additional structural mass has a performance cost that can exceed the benefit of the additional fuel. When you decide to add more fuel to a rocket, you have to add larger tanks to contain it. Those larger tanks weigh more. The turbopumps that have to handle the greater propellant flow rate have to be larger and heavier. The feed lines have to have a larger diameter and greater pressure capacity, making them heavier. The engines may need to be larger to maintain the same thrust-to-weight ratio. The rocket structure has to be more robust to withstand the greater weight and greater loads. And all this additional structural mass adds to the final mass of the rocket that is still present when the fuel has been exhausted, reducing the initial to final mass ratio and therefore reducing the velocity change that fuel can produce. This phenomenon, where adding fuel mass requires adding structural mass that in turn reduces the efficiency of the additional fuel, creates a point of diminishing returns that engineers have to carefully identify for each design. There is an optimal amount of fuel for each specific mission, and adding beyond that optimum produces returns that diminish to the point of becoming negative. Identifying that optimal point is one of the most fundamental optimization exercises in rocket design, and its solution requires simultaneously balancing the Tsiolkovsky equation, the mechanical properties of construction materials, the characteristics of available engines, and the specific mission requirements in terms of payload, destination orbit, and trajectory profile. Tank pressure is another factor that makes simply adding more fuel more complicated than it seems. A rocket's tanks are designed to operate at a specific internal pressure that is sufficient to feed the turbopumps stably and to maintain the structural rigidity of the tank during the maximum aerodynamic load phases of ascent. If you increase the tank volume to contain more fuel without changing the operating pressure, the total force that the tank walls have to withstand increases proportionally to the tank diameter, because the force due to internal pressure on the walls is proportional to the product of the pressure by the internal surface area of the tank. To maintain the same structural safety factor with a larger diameter tank, you have to increase the wall thickness, which adds mass in a non-linear relationship with the tank volume. This relationship between tank size and wall weight is another of the factors that make structural mass growth disproportionate relative to fuel mass growth when attempting to simply scale an existing design by adding more propellant. The aerodynamic stability of the rocket during ascent is also affected when, The mass distribution is modified by adding more fuel. The center of mass of a rocket shifts during flight as fuel is consumed, and the position of the center of mass relative to the aerodynamic center of pressure determines whether the rocket is stable or unstable during flight through the atmosphere. A rocket is aerodynamically stable when its center of mass is ahead of its center of pressure, so that any angular perturbation produced by wind or an irregularity in thrust tends to be automatically corrected by aerodynamic forces. If adding more fuel in a specific tank shifts the center of mass rearward beyond the stability limits, the rocket can become unstable during certain phases of flight, requiring more frequent and energetic active attitude corrections that consume additional control propellant and add load to the actuation system. In the worst case, the instability can become uncontrollable and result in the loss of the vehicle. The question of what type of fuel is added is another factor that complicates the equation significantly. Not all fuels have the same energy density per unit mass or the same density per unit volume, and these two properties have different implications for rocket design. Liquid hydrogen, which has the highest specific impulse of any practical chemical propellant, also has the lowest density of any propellant, approximately 70 kilograms per cubic meter, which is less than 1/10 the density of water. This means that to store a given quantity of liquid hydrogen, you need an enormous tank volume compared to denser propellants like kerosene or liquid methane. That larger volume requires a larger and heavier tank structure, which partially offsets the specific impulse advantage of hydrogen. This is why liquid hydrogen, despite being the propellant with the highest available specific impulse, is not necessarily the optimal choice for all applications, and why many modern rockets choose higher density propellants such as methane or kerosene for the lower stages, where tank volume has a greater impact on total structural mass. Liquid methane, which is the propellant chosen by SpaceX for the Raptor engine of the Starship and by several other rocket developers for their next-generation vehicles, represents an interesting compromise between the specific impulse of hydrogen and the density of kerosene. Methane has a vacuum-specific impulse of approximately 380 seconds, significantly higher than kerosene but lower than hydrogen, and a density of approximately 422 kilograms per cubic meter, much higher than hydrogen but lower than kerosene. Additionally, methane is easier to produce in situ on Mars from Martian atmospheric carbon dioxide and subsurface hydrogen, making it especially attractive for planetary exploration missions that require refueling at the destination before the return journey. The choice of methane for the Starship is not just an optimization of the physics of launch from Earth. It is also a strategic decision about mission architecture that goes far beyond the initial launch. Nuclear thermal propulsion is the technology that could most radically change the terms of this fuel paradox for long-range missions in interplanetary space. In a nuclear thermal propulsion engine, instead of chemically burning a propellant to generate heat and expel gases at high velocity, the energy of a nuclear reaction is used to heat a propellant, typically liquid hydrogen, to temperatures far exceeding what any chemical reaction can achieve, and that heated propellant is then expelled through a nozzle. The temperatures achievable by a nuclear reactor are significantly higher than those of any chemical combustion, which translates into propellant exhaust velocities of between 2 and 3 times those produced by the best available chemical engine. Doubling or tripling the propellant exhaust velocity in the Tsiolkovsky equation has an enormous impact on the mass ratio needed to reach any given velocity, radically reducing the amount of propellant a mission needs to carry from Earth to reach its destination. For missions to Mars or beyond, where travel times with chemical propulsion are months or years, Nuclear thermal propulsion could reduce those times to a fraction and make the transport of much larger payloads viable with the same amount of propellant. Ionic propulsion takes this logic to its most extreme conclusion within currently available technologies. Ion engines expel propellant ions, typically xenon, at velocities that can exceed 30 kilometers per second, between 7 and 10 times the exhaust velocity of the best chemical engines. This means that for any given velocity change, an ion engine needs a very small fraction of the propellant mass that an equivalent chemical engine would need. The disadvantage is that ion engines produce extremely small thrust on the order of millinewtons or centinewtons, compared to the meganewtons of the chemical engines of launch rockets. This means that ion engines cannot be used for launch from Earth's surface, where a thrust greater than the vehicle's weight is needed for it to lift off. But in space, where there is no need to overcome gravity immediately and where the time available for acceleration can be weeks or months, the small but highly efficient thrust of ion engines can produce velocity changes that would be impossible with chemical propulsion for the same propellant mass. NASA's Dawn probe, which visited the asteroid Vesta and the dwarf planet Ceres, used ionic propulsion to perform orbital maneuvers that would have been impossible with chemical propulsion given the mission's mass budget. What the fuel paradox ultimately reveals is that in rocket engineering, more is not always better, and that optimizing rocket performance is fundamentally a problem of finding the right balance among all the variables that interact in nonlinear and frequently counterintuitive ways. Additional fuel adds available energy, but also adds mass that consumes that energy. A more robust structure allows containing more fuel, but also adds dead weight that the fuel has to accelerate. A more powerful engine allows burning more fuel more quickly, but is also heavier and consumes more propellant from the turbopumps. Every design decision affects all the others through the inexorable physics of the Tsiolkovsky equation. And the rocket engineer's job is to navigate that multi-dimensional design space to find the configuration that maximizes mission performance within the constraints of physics, materials, and available budget. The next time someone suggests that the solution to a rocket's range problems is simply to add more fuel, remember that apparently simple question conceals one of the deepest paradoxes in propulsion physics. The fuel you add today is the mass you have to accelerate tomorrow. And in the universe governed by the Tsiolkovsky equation, every kilogram of added mass exacts its price in a way that grows exponentially with the velocity you're trying to reach. There are no shortcuts. There is no free fuel. There is only the physics and the engineering that learns to live within its limits in the most intelligent way possible.